Hello and welcome to another video on interconversions of carboxylic acid derivatives. And this is another video where we're going to look at using an acid chloride as a reactant. However, we're going to change the nucleophile. In a previous video, or the previous video in this series, I used acetic anhydride, a carboxylic acid as a nucleophile. Here I'm going to use an alcohol as a nucleophile. All right, and that's going to change the carboxylic acid derivative that we make. Okay, so the reaction we're going to look at in this video, we're going to take acetyl chloride and we're going to react it with ethanol. ET represents CH2CH3. And then this is often carried out with a base. Okay, some mechanisms might show us using a molecule of ethanol as a base, but we could also do this with pyridine. All right. And in our product from this interconversion, it's going to be an ethyl ester. So we're going to make ethyl acetate plus pyridinium chloride. Okay, we're going to make that salt. All right, so let's go over the mechanism of this reaction. Whenever you're trying to figure out the mechanism of an organic reaction, it's always good to think about the structure of what you have reacting. Okay, structure influences reactivity. Okay, and so what we have here is we have a carbonyl compound and with a pretty decent leaving group. All right, so this tends to undergo nucleophilic acyl substitution reactions due to the polarity of these bonds here. This is electrophilic, so it's an electrophilic atom. We have a lone pair nucleophile, and so that's going to influence the type of elementary mechanistic steps we want to draw. Okay, and so we're going to start with a nucleophilic addition. All right, so we're going to attack the carbonyl carbon. Nucleophilic addition, where our nucleophile adds to the carbonyl carbon. Okay, we formed this oxygen-carbon bond. All right, and then we're going to have a second step where that leaving group is going to leave. We're going to do a process that's the opposite of a nucleophilic addition. And we call that a nucleophile elimination. Okay. And so that will get us to here. So after two steps, we've done a nucleophilic addition and a nucleophile elimination. And we are left with an oxygen that has a positive charge on it. All right. And at this point, we're going to introduce, okay, in scene 3. Okay. Assuming I can draw a hexagon here. Maybe assuming a lot, but there's pyridine. That's our base. It's a lone pair. It's got a lone pair on it there. Bronsted base. Okay, we're going to pull off that proton. We're going to do a proton transfer, and we could also call this a deprotonation. All right, and that's going to get us to our ester. So I'll put up here. And then our byproduct is pyridinium chloride. All right, and so in summary, the 3 steps in this mechanism are a nucleophilic addition in the first step, followed by a nucleophile elimination, followed by a proton transfer. All right. And using ethanol as our nucleophile, we turned an acid chloride into an ester. All right, thank you for watching this video.